going to discuss in detail the two main popular approaches to set up an STM32 development environment using VS Code on a macOS. The first approach is based on a CMake project that is created by the STM32 VS Code extension. I think that this is the best approach for beginners that want to start writing and loading code to a development board as quickly as possible. The second approach is based on a Makefile project and requires more steps to get the toolchain configured and integrated with VS Code. This implementation is my preferred approach for small to medium-sized embedded projects. This is because it reduces a layer of complexity in the build management of the project. Also, by installing the toolchain from scratch, you will develop a deep understanding of how all the parts fit together. So let's discuss the CMake STM32 VS Code extension approach in a bit more detail. CMake is an application that runs in the background to automatically generate a native makefile based on the current configuration of the project. The STM32 VS Code extension will automatically create the basic CMake files required to build an example project. This can be used as a good starting template. So the pros of this approach are simplified project configuration. CMake offers a user-friendly way to define build settings and dependencies for different project configurations. Another pro is the cross-platform support. CMake is designed to generate platform-specific build files, which is good in larger projects targeting multiple platforms. So the cons are added layer of complexity. CMake introduces the requirement for an additional piece of software to implement the build system that builds the makefile. So let's discuss the makefile approach in a bit more detail. STM32 CubeMX will automatically create a basic makefile to build the project that has been set up in the cube. This is a good starting template to add to as a project develops. So the pros are reduced complexity. A simple handcrafted makefile can build a small to medium embedded project into an executable using a single makefile with minimal code. Another pro is the reduced software dependency. Using a simple makefile only requires GNU Make and not additional software to generate the makefile. The cons are project configurations. Different project configurations require advanced makefile knowledge to set up. In both examples, I'm going to show you how to take a Nucleo STM32 development board and set up a blinking LED project using STM32 CubeMX. Then we're going to run and debug in VS Code using both of the discussed approaches. In this video, I'm going to be discussing the Makefile approach in detail. If you think after hearing this that the CMake STM32 VS Code extension approach is more suitable for your application, then click on the link to this alternate video in the video description. Okay, let's get started. Okay, so I'm going to show you how to download STM32 CubeMX. So we're going to go to www.st.com. Then from the search bar on the top of the website, we're going to type in STM32 CubeMX. Then select it from the list. Scroll down to Get Software and select the latest version for macOS. Accept the license agreement. If you've got an account, then log in to download. If not, then enter your credentials for a one-time download. Okay, so once STM32 CubeMX is downloaded, there's a little bit of a trick to get it installed on a macOS. Basically, we need to change the permissions of the files in the installer. So to do that, we will change directory, pop in the root of the downloads. We want to change from this directory onwards, so we're going to type in sudo xattr and then that directory. Okay, now that we've done that, we can come back up and double click on the installer. Accept the license agreement. Okay, so that's all done, and we have to give it full disk access, otherwise it won't launch. So we'll give CubeMX full disk access. Now we can launch the app. So now I'm going to show you how to set up a basic Blinky LED project using STM32 CubeMX. Now the development board that I've got is a Nucleo 64 for the STM32 F070. If you've got a different Nucleo board, because there's lots of different types, and you want to follow this example, then key in the part of your development board. Okay, so to get started, I'm going to go to File, New Project, and then in the commercial part number, I'm going to type STM32 F070. And you can see it's found it there, and it's referencing the Nucleo development board that I've got. So I'm going to select that and go Start Project. Okay, so the first thing to do is come along to the system core on the left and select the sys from the drop down. And what we want to do is turn on the debug serial wire, which is the SWD peripheral, and that allows us to run code and debug it. So we definitely want that turned on. And now I'm going to come into the GPIO to set up our LED. So if you have a look at the schematics for the Nucleo development board, we can see that there's a LED called LD2, which travels all the way back through SB42 to PA5, which is on the micro as PA5. So what we want to do is select PA5 on the chip, select it as an output, and we want to change the user label to LED LD2 so we can identify it in the code. Okay, so the next thing to do is to come into the project manager, and then for the Toolchain IDE setting, select Makefile, then go up to File, select Save Project As, and we're going to put it on the desktop, and we'll call it Blinky STM32 F070, and we'll save that, and then we'll generate the code. Now I'm going to show you how to download GNU Make. Now the best way that I think to download GNU Make is to download a package manager for macOS called Homebrew. So to install Homebrew, I'm going to copy this very ugly link in that you can get from the internet by googling install Homebrew macOS. Okay, the key thing here is that it's going to install Xcode command line tools. Now Xcode command line tools automatically bundles in the installation of GNU Make, and that's what we want. So when you run this script, it's going to take about 5 minutes to complete. When it's finished, you need to test that GNU Make has installed correctly by doing the following. Make version, and I can see that GNU Make has installed on my computer. Okay, we're going to download the ARM GNU Toolchain, and to do that we're going to open up a new tab and type in developer.arm.com. Then we're going to go to Tools and Software, close this preview pane and scroll down to ARM GNU Toolchain Downloads. Okay, the version that I've tested this tutorial on is the December 22 12.2. So let's open that up, and you'll find the first thing you'll come to is the MinGW for Windows versions. Then we get to macOS. So we need to choose between the x86 Intel architecture or the Apple Silicon, depending on your machine. Mine's an Intel architecture, so I'm going to come down into this section. Now the next important thing is we want the embedded ABI architecture. Download the one with the installer, which is the one ending in .pkg. So I'm going to click that, and then once this downloads, I'm going to show you how to run the installer and install it. Okay, so let's install the ARM GNU Toolchain. So to do that, navigate to your Downloads folder and double click on the package to run the installer. Step through the installer. Okay, so once the installer has completed, navigate to your Applications folder, and you'll see that the ARM GNU toolchain has installed here. So what we want to do now is set a path environment variable so that the operating system knows where to find the compiler when the Makefile calls it. Open up the Toolchain directory. Keep opening up the directories till you come to the binary directory, and then you can see the GCC compiler here. So to set a path variable to the compiler, come down to the terminal and type the following. So sudo nano etc pars. A good trick to get the path of the compiler is to press Option Command C. And then back to the file, and let's paste that path. And importantly, we need to remove the executable from the path. Control O and Control X to exit. Now let's open up a new terminal and check that we can get the version of the compiler to check that the path variable worked. So type the following. And you can see it's all working fine. Now that we have the toolchain installed, we are going to build the Blinky project. So to do that, if you look inside the directory, you'll see a Makefile. If we come down to the terminal and change directory to where the Makefile is, and then we type make, we can see it compiling the source, and it's linked it, and it's generated the ELF file, the hex and the bin. So I'm going to install OpenOCD. OpenOCD stands for Open On-Chip Debugger, and basically it's an open source software tool used for debugging and programming microcontrollers. So the best way, in my opinion, to install OpenOCD is to use Homebrew that we installed earlier. So if you type in brew install OpenOCD, it'll go ahead and install it. So basically OpenOCD has lots of config files for the many adapters that are out there, J-links, ST-links. It has config files for the interface that's used to talk to the MCU, whether it's single wire debug or JTAG, and it also has config files for all the different MCUs. Its primary role is to host a GDB server using GDB GNU program that we installed in the toolchain. What it does is create a client, which we call a GDB client, that opens a TCP socket to that server. Once you've got that socket open, you can load in an ELF file, which is basically the file containing debug information. So let's download Microsoft Visual Studio Code. To do that, let's open up a new tab and go code.visualstudio.com. Download the Universal Mac build. So when the Visual Studio Code download completes, the first thing to do is to go to your download directory and move the app into the applications directory. Once it's there, launch it, then go up to the View menu and go down to Extensions, type in C, C++, install the one by Microsoft, then type in Cortex Debug, then install the one by Maris 25, so we're going to set up VS Code for GDB debugging. Now the first thing to do is to open the STM32 Blinky project that we did earlier. So I go to Open Folder, Desktop, Blinky, make sure it's the root and the Makefile is under that or below that. Then we want to go to Run and then go Add Configuration. Select Cortex Debug from the drop down up here. This is where we need to change some parameters. So the first thing is to scroll down to the executable line and remove that. And we want to put $ brackets workspace root / build. We want to look what the name of the ELF file was that we built, and so we key that in. We go Blinky STM32 F070.elf. The next field to edit is the server type, and we want to change that to OpenOCD. Now we need to add 2 more fields underneath, and the first one to add is the device. And the last field is the config files for OpenOCD. So inverted commas, config files. Now this one is the OpenOCD interface for ST-Link. And the next one is the target MCU on my Nucleo development board. And then save it. And that's the launch.json file set up. So now we're ready for the most exciting part, and that's to add in the LED Blinky code. Expand on the source directory, select main.c. Now we're going to scroll to line 75 or 76 and add the following code. So uint32t timestamp then down to line 95, and we're going to add this code. So this basically looks for the system clock advancing by 500 milliseconds, and if it does, then we'll toggle our LED. And to toggle the LD2 LED, we'll use this HAL command, gpio toggle pin. And we called that LED LD2. And then we need the pin. Okay, and I missed a bracket here. And I think that is happy now. So let's save the file, go to terminal, and let's build it using the make command. And that looks good. So the next step is to connect the development board to the computer. And once that's done, head on over to the run and debug button, hit the green play button. So you can see we've hit a breakpoint at the main entry point. So that's good. So that means the OpenOCD server has accepted the client connection. The ELF image has been flashed in, and basically when we hit continue, we should see the LED flash. If I scroll down, I'm going to set a breakpoint, then we can step into the code and observe the registers. So now if I take the breakpoint off, the LED will blink indefinitely at 1 Hz.